Section 6.1 is slope fields. So this is a new topic for us. We're going to start by reviewing differential equations really quickly. So let's take a look. Determine whether or not a function y satisfies the differential. So here's our differential. To solve a differential equation, we have to separate the variables. So I go from dy dx equals 3y. I'm going to divide both sides by y and multiply by dx. And if you remember, we integrated both sides. So I have ln y equals 3x plus c. To solve for y, I'm going to exponentiate y equals e to the 3x plus c, which is e to the c times e to the 3x. And e to the c is some constant. So yes, this could satisfy the differential equation. Try 2 and 3 on your own real quickly, and then we will look at those together. Okay, so number 2, working the same method. There's only x's here, so I can leave everything on the right. dy equals negative cosecant squared x plus 5 dx. I'm just looking for the antiderivative. So y would equal cotan x plus 5x plus some value c, so 3 is fine. The last one, if you tried it, y dy equals dx. Again, integrating both sides, I get y, antiderivative of y would be 1/2 y squared equals x plus c. I think we can see that by doing both of these sides, multiplying by 2 and taking the square root, I would not get this expression. So the first two are true, the last one is not. The other thing we have to do in this section is to talk about finding c. So using an initial condition, so if my antiderivative is y equals 4x to the 4th plus 2x plus c, I'm going to go ahead to the solution screen because this is just plug and chug. So we let y equal 5 and x equal -1. Solving for c, we get 3. So my general solution is this. My specific solution would be y equals 4x to the 4th plus 2x plus 3. Same thing here, using an initial condition, plugging in -2 for y and 0 for x. I get c equals -3, and my specific solution would be, -3. Okay, so just a quick review of looking at differentials. So let's move ahead and talk about differentials in another context. An equation solving a derivative is called a differential equation. The order of a differential is the order of the highest derivative involved in the equation. We'll talk about this again in a minute. Just jot that down. So we want to find all functions y that satisfy dy dx equals 3x squared plus cos x. So again, we are going to find antiderivatives. Since this is just in terms of x, we don't have to do any implicit work. So the integral of dy, which is y, is the integral of 3x squared plus cos x dx. Looking at this, we find that the solution can be any antiderivative of the form x cubed plus sine x plus c. So that's a general differential solution, like we did in our preview. First order differentials. If the general solution to a first order differential, that means just dy dx, okay, a second order would be d squared y dx squared. We've talked about that before. The only additional information needed to find a unique solution is the value of the function at a single point, called our initial condition. A differential equation with an initial condition is called an initial value problem. it has a unique solution called the particular solution of the differential equation. All right, so find the particular solution of dy dx equals e to the 2x minus 3x. This graph passes through the point 1, negative 2, this being our initial condition. So the general solution, differentiating both sides, taking the antiderivative, we get 1/2 e to the 2x minus 3/2 x squared plus c. Putting in the initial condition, 1/2 goes in for y, 1 goes in for all of my x values. I can then solve for c, adding 3/2 to both sides and subtracting the negative 1/2 e squared. So all of this is my value for c. I tack it on to the end. So c doesn't have to be necessarily a single value. It is a constant. This is a number, but we can have it in terms of e or in terms of a radical, anything like that. Okay, another way to solve an initial value problem is to use the fundamental theorem. So we want to find a solution again to the differential equation f prime of x equals cos of x squared, for which f of 3 equals 5. So if I use the fundamental theorem and write this as an integral from 3 to x and put a plus 5 on my equation, now if I solve this for f of 3, it would be the integral from 3 to 3 of cos t squared dt plus 5. This is 0, and I do get f of 3 equals 5. So by manipulating the limits of integration, I can create an integral solution to this initial value problem, just like I created an irregular equation. Okay, so 2 ways to solve our initial value problems. We'll do some more work on this, but now we're going to go and move on to our slope fields. So the differential equation gives the slope at any point x, y. So when we have dy dx equals 3x plus y over y squared, if I know a particular xy value, say 1, 2, I can find the slope, dy dx, would be 3 times 1 plus 2 over 2 squared, or 4, would be 5/4. So given any ordered pair and a differential equation, I can find the slope at any point. Now this information can be used to draw a small piece of the linearization. The slope at this point is 5/4, which approximates the curve that passes through that point. Repeating that process at a lot of points yields an approximation called a slope field. Let's do one together. So we are going to construct a slope field for the differential equation dy dx equals cos x. Since the differential is just in terms of x, any point that starts with 0 will have the slope that is cos of 0 or 1. So if I plot those, any place that x is 0, and put a little tiny slope of 1, because remember that slope doesn't go on forever for this equation. It's just at that point that is the slope. Then we can go on. The slope at any point pi comma y or negative pi will both yield -1, because the cos of pi, using my differential equation, is -1, and the cos of negative pi is -1. So I can plot those at pi and negative pi. Notice that my scale here is from -2 pi to 2 pi. So at pi and at negative pi, I have slopes of -1. The slope at all odd multiples of pi over 2 will be 0. So pi over 2, 3 pi over 2, 5 pi over 2, etc. So again, at these middle points, I'm going to get 0 slopes. And any place along plus or minus 2 pi, 2 pi, 4 pi, -2 pi, -4 pi, the cosine of those values is 1. So putting those in at the far reaches. So this gives me now a slope field for the function cos of x. And depending upon what my plus c is, because the antiderivative of this represents the function y equals sine x plus c. So let's say that c is 0, starting me at 0, 0. At the point 0, 0, the slope is 1. It goes up. The slope then, you can see, then will become 0. Then it moves towards -1, then 0, then 1. And you can see that what I have here in this slope curve is a rough pathway to show the function of sine x. If I choose to start at the point 0, 3, meaning that sine of 0 is 0 plus 3, then it would be the function sine of x plus 3. But again, the slope fields would give me the same appropriate sine function. So a slope field kind of gives you an idea for how the curve is going to look that has this differential equation. Let's do one more together. Oops, where'd my other slide go? Well, let me see if I can get a blank slide. I don't know if I'm going to be able to. All right, let's use this. Put a blank slide. And what I want you to do is to put a couple of dots to represent where we are going to show our slope field. We're not going to do a whole bunch of points. So this is like a graph, but we're putting dots at particular points on the graph. All right, and we'll do some of these together as well. I apologize for not having the other slide. So let's say that dy dx equals x plus y. Now, my slope is dependent upon both x and y, but let's try a few points. So let's find dy dx evaluated at 0, 0. So at 0, 0, my slope is 0. Let's do dy dx evaluated at 1, 1. Now my slope is 2, so at 1, 1, my slope is going to be a little tiny line that would indicate going up 2 into the right 1 or down 2 into the left 1. So it's going to be a pretty steep little line there. Try a few others. Find dy dx at -1, 2. Find dy dx at -1, -1. And let's find it at -2, 1. So at -1, 2, it's going to be dy dx going to equal 1, adding those together. So at -1, 2, my slope is 1. At -1, -1, I'm going to get -2. So at this point, again, it's going to be a steep negative. At -2, 1, we are going to have a slope of 1. So it's going to look like that. So what I would like you to do is to continue filling in this slope field for all of the values from -2, 2, 2, 2. So a grid that is 4 units high and 4 units wide. So fill in the rest of these slopes and come to class with a slope field to represent this dy dx or differential equation. All right, that's it for now.